Well, welcome. Thank you for coming to this Director's Special Colloquium. It's really my pleasure to welcome Charlie Catlett back to NCSA, something I don't always get to say. Charlie is currently a senior computer scientist at Argonne National Laboratory, as well as a senior fellow at the Computation Institute at the University of Chicago in Argonne, and founding director of the Urban Center for Computation and Data. He currently leads an NSF-funded Array of Things project, establishing a network of 500 Argonne-developed intelligent sensor units in Chicago, which I think we see image there. And he is, as I mentioned, he's an alum of both NCSA and computer engineering here at Illinois. And I'm also told he has a frightening picture of a bunch of us, which I hope to see. So with that, Charlie.
Thanks. Well, thanks for coming. I'm really excited to be back here and spend the day. I don't get down here that often, but I already have had 2 meetings this morning and have planned 2 meetings in Chicago to try to build some collaborations. I want to just kind of talk to you about what I've been doing for the last 5 years or so. I did high performance computing for 25 years, and then I made as Bill can attest, the dubious decision to be the CIO for the lab. And I figured out in time that was a bad decision, but it was too late, and I was starting the next week. So after doing that for 4 years, I got the chance to reboot. And so rather than just kind of like go back to what I'd done before, I was really interested in cities. And, you know, we work right outside of a large city. So I started to look for opportunities to connect computer science and computational science research with challenges that actual cities have. So I spent a lot of time, and I still spend a lot of time, just going into people's offices who work for cities, usually it's Chicago, not always Chicago, asking them to tell me what their challenges are. And then I kind of try to connect those challenges to either stuff we're doing or stuff other people are doing. So I want to tell you about the Array of Things project. It is the thing I spend most of my time on in both absolute and relative terms. But I want to also tell you how we came to do this project and why we're doing it, because we're not doing anything that didn't start with one of those conversations with someone in the city of Chicago where they said they needed something and we responded with something. So we've never actually gone into the city and said, look at this cool thing that we've done. You could really use this cool thing that we've done. It's always been, okay, that's your need. Well, we have kind of something like that. Maybe we can adapt it to what you're doing. So it started out with data infrastructure and data analytics. We started to do some computational modeling after doing some a few years ago, and we started again as part of the Exascale project. And then the Array of Things project, which is trying to build a measurement infrastructure at a city scale. As Bill said, I did come from here. That's me with the first Cray system. A couple of the directors there, proudly standing next to the CM5, and then we had as some of you remember, when we would close a machine down, we would have sort of a wake for it, and Larry got to throw the last breaker on the back of the CM5, but several of us got, so that's me throwing the breaker on turning off the CM5, which was a sad day, because that was a really cool machine. Then I found this in a folder the other day, and I'm just kind of wondering, like, how many people in the room are in this picture? So I'm in the picture. Ed, were you there? I remember. Yeah, so here's Melanie is here. Ralph Roski's when he was young. Dan and Bill and Rick and me. Here's Rusty. Carl and Ian, there's Ian right there. Anyway, I found this and took a snapshot of it. That's before color film. But before color film, yeah. This is right before we got in the carriages and took the stagecoach back to Illinois. So one thing that I started to learn really early on when we were looking at doing work with cities is that I tended to think of cities as these big sort of monolithic things. And in fact, cities are just collections of neighborhoods. And neighborhoods and districts are collections of neighborhoods, and cities are collections of districts. And where you live in a city makes a huge difference what your experience is. And I'll just say, part of my motivation is I really want to use what we do to make this city and other cities work better for some of the people, for the people that live in them. So when I look at this, I go, wow, you could, depending on the neighborhood you live in, your life expectancy could be 15 years different than some other neighborhood. That's like appalling. Philadelphia, the map shows a 20-year difference. And then on the middle one there, it does say the red ones are over 20% asthma, of people have some form of asthma. In fact, if we went to a finer color scheme, there are neighborhoods that have over 40% of asthma incidents in Chicago. And again, not different than other cities, I just happen to have maps of Chicago. If you use Google's tools, you can figure out how long it takes to get to the Chicago Loop from different parts around the city, and you get this map on the right-hand side where it's pretty clear that some places are going to give you more opportunity for things like jobs than other places, because you can get into the loop where many of the jobs are in 30 minutes instead of an hour and a half by public transit. So these are some of the things that motivated us to help the city do analytics to see, well, what could we do if we knew more about these challenges? How could we improve the experience of people living in cities? The city, like other cities, has published an open data portal. This has now been around for almost a decade, and there are hundreds of cities that have these, in counties and states. And people would go in and make these kind of maps like this, or in this case here, it's a movie that's not playing, but these are snowplows moving around during a snowstorm. So you can analyze what we did an analysis one time based on GPS data from garbage trucks. We did an analysis of whether the new garbage pickup schedule for the city, and this is 600 square kilometers, whether that was better than the old one. And better meant fewer miles driven, less impact on traffic. Fewer miles means less fuel and less emissions. And so we're actually able to do that analysis. And so part of what we're trying to do is give the city the ability to make data-driven decisions and then use data to analyze the outcome of the decisions that they make. I like to use this example of what I mean by using data to improve something about the city. The City of Chicago has 15,000 restaurants and grocery stores and food establishments, and 35 inspectors that need to inspect those 15,000 establishments every year. So the Commissioner for Public Health came to the Chief Information Officer for the city and said, can you help me improve how we do this? So the city, this is before our involvement, the city worked with Allstate data scientists to do something pretty straightforward, which is to say, let's analyze all 15,000 of those restaurants or food trucks or whatever they are, and let's rank them according to risk, the high, medium, or low, a high, medium, or low risk of having a food safety violation. And then let's inspect based on risk. So everyone still gets inspected, but the order is different. They did a 60-day double-blind trial that you see here over 60 days, and each the inspectors were divided into two groups. One group was told, do your random inspection as usual. The other group was said, here's a list, don't ask us what it means. And the blue one is the one that is the ordered one. And on average, they're finding violations about a week ahead of where they would otherwise. That is a long time. That is a lot of people going through a restaurant or buying groceries. Now, we brought in the team that Bill came from, the applied math guys at Argonne. And by the way, we brought some folks in from DePaul and UIC and UChicago as well to start working with the city and to find problems like this and see if we could help. So we brought Sven and Prasanna in, and they were able to push this from 7.4 to 8.4 days, which astounded the chief data officer for the city, because he'd been putting this out as a challenge and people were coming back with 7.5 or 7.6 days. So he was like really amazed. But the thing that they did that was even more impactful, I would say, is that they showed a way that we could shorten this timeline from the commissioner coming and saying, can you help me, and having an operational improvement in the system. And they did that by essentially sort of turning machine learning back on itself to use machine learning to choose the leading indicators and to develop the model, and then shrink this period here, which would typically be done by a data scientist working with some inspectors or what have you. So by shrinking that, it means that the city, with its modest number of resources, and Chicago has a lot of resources compared to other cities. I'm going to bet that Urbana does not have a chief data officer. If they do, he or she is probably in charge of 6 other things as well, but they probably don't have a data science team. But even a large city, there are just so many projects to get through that this kind of shortening is really a breakthrough. One of the things we also noticed is that people were making maps, and that social scientists or economists who might want to use the city data didn't have a way to even know it was there. So we built this with this thing you're seeing here with some NSF eager money, an eager grant. We said, how about if we build a geospatial database, suck in data from all open data portals that we can find, make that that ingest process configurable so we can like update every day or do a differential update or whatever. And then let's put some APIs on it, but we'll pull all the data together on a single timeline and with geospatial references. And now you draw on the map, you give it a range of dates, and this is showing all the data sets that we found in the database. And we're talking about food safety, so we're clicked on the food safety inspections, and this tells us for the Hyde Park area around UChicago, which is where I drew the box, it tells us the number of food safety inspections that happened. But, and I can change the resolution, but I'm really interested in food safety, so I can then go in and refine this search and say, now show me only the inspections that were triggered by a complaint. And once I find those that are triggered by a complaint, I can refine it a little more, and then I can download the data and go analyze it. This is not an analysis system. Or I can grab these URLs, these endpoints, and just stick them into some application or another portal. So the first thing then that we wanted to do was to just make the data available and do some integration to reduce the amount of work you have to do to just do something like ask a question like, how does weather affect crime? You have to go out and get weather data, you have to go get crime data, you have to like merge it together somehow, and then you can do ask your question. So we were trying to reduce that upfront amount of work so people could ask more questions. The city used those same APIs to build this thing called OpenGrid, which is the same back end, but this now is optimized not for a policymakers, or an economist, but for the general public. So these two things together, the first is called Planario, and then OpenGrid are now sort of one-click installs in AWS for any city that wants to put this kind of infrastructure in. It's all open source. So I mentioned weather and crime, partly because we drove the development of Planario with 2 projects, one of which was this crime prediction project that was led by Brett Goldstein, who at the time we did this project was the chief data officer for this, or chief information officer for the city. Prior to that, he was chief data officer for the police department, and prior to that, he was walking a beat on the west side. He decided to do that after going out and doing the open table startup for some reason, then became a cop. So quite an interesting story, but because he came from the police department, he said, we think that in general, the first warm weekend of the year, we're going to have more shootings than normal. But we don't know where, but we know that happens. And so he wanted to validate some of his predictive algorithms with respect to crime to say, could we go back over the 8 or 10 years of crime data that we have, and could we first predict crime over a 72-hour horizon, hour by hour, for that part of the city? This is 866 census tracts of the city. And then if we add weather as a leading indicator, do those predictions get better? So it turns out they do, and it has to do with like a 5 degrees C increase over a period of 2 or 3 days. We don't know why it is, but we at least were able to say, yes, weather does impact people's decisions. And if you look at the literature about air quality, you find the same thing. So unfortunately, although we had all the addresses of the crimes that happened, and we could use that data to validate the algorithms, we only had weather data from 6 stations around the city. So we didn't have high-resolution weather data, and air quality data is, not much better. So there are like tens of square miles of the city that don't have air quality data. So the kind of modeling that I just showed you is the short-term stuff. I want to mention, almost as an aside, but I'll just mention, we're also looking at long-term models. So this is the North Branch framework in Chicago on the North Branch of the river. You can see it here. And the city has just almost unanimously passed a plan to redistrict and rezone that and spend a few $100 million on redoing the area. So they've done analysis of, where the jobs are. You can see in Chicago what's happened here, a 261% increase in info and tech jobs, and then even more in this sort of B2B area here. And so part of that is rezoning, part of it is making sure you don't lose businesses by moving them to a different district. And to do that kind of project, the city, it's the Department of Planning and Development, the city looks at land use over time, it looks at green spaces and historic buildings and transportation and sewer and water and energy, and then they get bids that come in from developers saying, if you give us $150 million, you get something like this. We were meeting with with the deputy commissioner, and she said, maybe I'm crazy, but I would really like to know, before I do something like that, how it's going to affect transportation and the electricity grid and the sewer and water networks. And even more, maybe I'm really crazy, she said, I'd like to be able to make those buildings larger or smaller and see how that impacts the district. Not over 72 hours, but over like 72 months or maybe even 20 years. So I said, I hope you're not crazy, because we just got this funding from DOE to do something like that as part of the Exascale program. So we had done some projects before, about 5 years ago in Chicago, looking at about a square mile of redistricting, or actually building from brown space, and what would be the energy demand for that square mile as it grew from 0 inhabitants to 100,000 inhabitants over 20 years. So we started to look at weather and building energy models and putting them together, but all of these kind of projects take one model and another model, and they develop this bespoke system for putting them together. And so we said, what we would really like to do is to be able to connect n different models for different questions, so that you could do a more holistic simulation of something like the North Branch framework. So what we're doing now is just a small project that started up last year, and we're in the second year that just started, of putting 4 specific models together and trying to understand how these models communicate to one another, what content needs to go between the building model and the atmosphere model, or between the social economic model and the transportation model. What's the volume and content of that, and what are ways that we can sort of take advantage of tools like this? I'm not going to go through this hairball, but just to show you, take advantage of tools like this to put these models together, and then cope with things like this model here. Even if you've got 100,000 buildings, it's still going to run way, way faster than this model over here. And so you've got to sort of compensate for that. And that was part of that was why we decided to try to go with this asynchronous approach. What I'm showing you here is not real. What I'm showing you is a plan, and a plan that we're sort of marching on in the next couple of years. So that's the sort of long-term modeling. Now, how do we get from this to things like array of things? You remember that ASMA diagram, and some of the big red areas were like here on the south side and here on the west side and the near west side here, where we have 0 information about air quality. So 4 years ago, when we had this, it was actually almost 6 years ago that we first started thinking about maybe we could put sensors across the city of Chicago. 4 years ago, we started having these workshops with different science communities saying, first to the environmental and weather guys, hey, if we could put a couple hundred devices across the city of Chicago to measure something, number one, what would you like to be able to measure? And number two, how do we do it in a way that's scientifically useful to you? And we learn things like, well, we don't just want temperature because we don't know if that temperature is being taken in the shade of an oak tree or in the middle of a parking lot. So we need more than that. We need ambient light and other things. So what happened over a period of time was we started to collect and sort of do the analysis. Can we get a sensor like that for a couple $100 rather than a few tens of thousands? And would it be a reasonable quality? Came up with a configuration that's out in the system now. But when we were talking with the transportation guys and social scientists in particular, and my original plan was no cameras, I didn't want to deal with the privacy issues. They finally, like my elbow was about to be, break from being twisted, they finally convinced me to do cameras because they said, well, we want to measure, you can't buy a sensor for it. We want to measure the stickiness of a park or the flow of pedestrians. We want to know not just how many vehicles go through an intersection every 30 seconds, but how they go through, how many of them turn left. And even more, if you look down the road, some of the transportation research guys people were saying, well, could we even detect a near miss, that a car screeches to a halt but no accident happened, and so did it really happen, right? And could we even go a little bit further and say, could we imagine doing research into the idea of an intersection that had some reflexes to it that did the right thing when dangerous things happened? Whether that's, we noticed that there are 400 pedestrians waiting to cross the street and one car is coming, so maybe we turn the light for the pedestrians because one of them or two of them are going to run in front of that car, and over a course of time, people get killed that way. Or maybe we see a car that's speeding so fast that it's never going to stop for the red light, and so we're going to wait before we turn the cross street green. So if you want to do that kind of research, there were two things that changed about the platform that made it harder from a technical point of view and from a policy point of view. The camera added complexity with respect to policy. The fact that we wanted to get an answer from the intersection in near real time meant that we had to put computing out there. So that made it a lot more difficult in terms of technology and making a system that could live on the street corner and could have computing that we would remotely program it and that we would never have to go out, or at least rarely have to go out and press a reset button. By the way, the notion of a near miss is something every city that we know is interested in, because if you look at a city like Chicago, there are a lot of cities that have this program called Vision Zero. Vision Zero in Chicago is eliminate traffic-related fatalities by 2022. So that's 150 people a year that get killed from being hit. They're pedestrians or bicyclists or people in cars. In any safety program, it's not enough to just know where people got killed. You want to know where people almost got killed. And so the near miss is a really important capability, and one that we can't do with the power that we've got in the device now. The processor we're using for machine learning here is about as fast as an iPhone, but the version next year will be much, much better, as you see if you watch what's happening with machine learning hardware. So we got a grant from NSF. It's a major research instrumentation grant for $3 million. We had partners that I listed on the title slide. 7 companies came in to do in-kind cost share. The city of Chicago said, we will mount these things and not charge you. That's a huge cost share. If you think, you can do the math, it's a crew of 3. They cost about $125 an hour. They got to go out with a bucket truck and spend a couple hours putting these up. So that's a huge cost share that's really enabling us to do this project. The instrument that we're trying to build, which is an experimental instrument, and we think it will be useful, but we'll see, has to do 3 things. One is the traditional sensing. That's pretty easy to do. Literally, these are high school, projects doing sensor networks like that. And putting sensors in as they become cost-effective and available, we put them in and just collect that data and send it back for analysis. We also wanted to evaluate new sensor technologies. Here it gets a little bit more difficult. We're dealing right now with these gas sensors are printed electrochemical sensors, and it's very new technology. The companies that do this are the small companies that have things like we're dealing with a 5-month delay on one of our boards right now. because we're trying to be at the really bleeding edge there. But we wanted to build a system that would allow us to inject new technology like that. And it might not be a sensor, it might be a radio, it might be a computing system, might be a new kind of camera. And we wanted to be able to inject those. So our design, one of the boards that we designed actually allows us to hand solder extra sensors to it if we wanted, just to try them out. We have in this, in the blue boxes, the top 2/3 is where we've got a supervisor board that keeps 2 Linux devices healthy, and allows us to unbrick them if they get bricked, and allows us to shut them down if it gets too hot, so that they don't burn out, and then bring them back up again when it's cooler. In the white part here, there's a harness that hangs sensor boards. There's a camera here. There's a camera here that looks up that does these things. And this is designed for us so that we can add layers and make that longer. So we can also inject into the city devices that ideally aren't much larger than a hockey puck, because that will fit nicely into that 3.5-inch cavity inside there. And then the really challenging thing is what I mentioned before, is trying to detect conditions, whether it's flooding or bicycle traffic or what have you, using machine learning inside the box. And this, it turns out, is what most of our work is focused on, and what we hear from people is the most interesting thing when they say we want to use your stuff. So we're focusing a lot on the whole notion of running a system here where you can stick new classifiers and other algorithms over time, and then unbrick the machines when inevitably somebody does something, maybe even us does something wrong. Just one example, you see this is a bicyclist here with a helmet on. Besides near miss, and just like we had these scientific workshops, we've talked to over 100 cities about this project. And Portland came up with what I hadn't thought of, but they came up with what I think nicely illustrates the need to do something like this rather than just a straight sensor network. They said, we have a bike share program. It's great, people are out on bikes, it's good cardiovascular exercise, but we think it might be encouraging people to ride without safety equipment, without helmets on. We don't really have a way to measure that, short of putting somebody on the corner with a clipboard. So they said, could you differentiate first between a private bike and the bright orange Portland bike share bikes? And then could you go one step further and determine whether the rider is wearing a helmet or not? And we said, that's probably almost certainly more than we can do with the current device, but not more than we can do a year from now. So we're starting to sort of line up these types of machine learning problems, and ideally what we want to do with the project, besides just run an instrument like this, is to use this capability to connect social scientists, or I'll say non-machine learning people, with machine learning people, so that you could say, I have a new theory that a neighborhood, I can measure how safe people feel by counting the number of people walking dogs or babies. So I need a machine learning person to help me do the dog and baby walker classifier and put it out in your device. So lots of opportunity there for things that we haven't really thought of. This is just a sample image, so you can see it's a 5 megapixel camera that's pointed straight down. This was one of the first ones, and we looked at it and we went, oh, maybe we should make it landscape mode instead, so the new ones are 90 degrees turned. But that's roughly what we can see. You can read all about the privacy policies on our website, but in a nutshell, all images stay inside the device, get analyzed, and then they get deleted. So we're not pulling surveillance camera images or video back to some central location. But we can do sample images and sample sound clips and pull those in, as long as what we've said is we will treat them as if they had sensitive information, so controlled access to them, you have to sign a data use agreement, et cetera. So we've had some students working on stuff, that I think this maybe I would say this is sort of like the hello world of machine learning. Can you classify pedestrians, or can you track one through the scene? So we've just had a team of grad students over the summer just kind of looking at what we could do. Flooding is a big problem in lots of cities, including Chicago, and it's a huge inconvenience, but it's also just a huge financial issue. And so we wanted to be able to detect standing water at intersections. And so our students came up, or I don't know if they came up with this, I suspect not. I would have done, I would have done an edge detection. They said, well, the surface of water always moves in a sinusoidal way, so we'll just take a burst of 50 images and analyze that, and then we'll be able to tell what's water and what's not water, which I thought was, I mean, maybe they read it in a paper somewhere. I thought that was clever, non-intuitive from my point of view. And then I keep mentioning, like, the part about putting sensors out there into the city, I mentioned some ways that we can do that. We're also staging these devices out. So 100 of them are scheduled to go out in the next few months. We had only about a dozen or two over the winter last year, and then 200 a year from now, and 200 maybe 18 months from now. So those are kind of launch windows where you can put a new device in. And one of the things that we're looking at right now is what to do in terms of the machine learning capability and what we do to replace the one that we've got there. And we're talking to ARM and NVIDIA and Intel about just that. So that's why, this current system out there is interesting. The one we put out next year will be much more interesting from the point of view of machine learning. All the data is free and open. That's both according to the cooperative agreement with NSF, and the policy of the city of Chicago is all their data with respect to not private data, but all the data like this is open and not monetized. It all comes into a set of databases that we run. We have concentrated on this pipeline here, not on how it gets used by scientists. This is where we want to find partnerships with other groups to both build portals with the APIs that we provide, and also to build applications. I'm not paying attention to the time, and I don't see a clock. Oh, 11:35. When do you want me to stop? Oh, okay. All right. Good, because I'm talking about my baby here. I mentioned that sensor networks are easy, and they are. So a sensor network, this is the board that we designed. And if I had the resolution, you see these holes right here, they say things like I squared C 3.3 volts and serial, and I squared C 5 volts. So this board has a set of commercial sensors here with these holes to do thermal isolation from the processor. And then we can solder other sensors that weren't available. But if we want to respin this board, it's just like an 8-week turnaround. So it takes about 2 weeks to get a sample back from the fab. We test it, we send it back to them, and then they hit print, and we can have as many as we want. It's actually also not that expensive. So we've got a couple of ways to add sensors here, but to do a sensor network, you just have this cheap, very durable processor. You program it once to sample the sensors and then send them through a modem to some data system. You can build something like that that's super reliable. I have something like this in my basement. I haven't had to reboot it for 2 years. That's watching my appliances for me. I admit that's a weird thing to do, but maybe in this room there are other people that like to do stuff like that too. So it's easy to do that, but when you add the programmable devices, then things get interesting because people will brick them, you will brick them. We've had instances where we've corrupted the SD card and corrupted the file system because somebody made a program mistake in our software without even turning it over to end users. So what do you do when that happens? We first thought, well, we'll put like a garage door opener thing in there. I mean, we actually thought about this, and we'll drive by with a garage door opener to reboot the machines when they need to be rebooted. So what we ended up doing was building this supervisor board. It's called this is the Waggle platform, is what the internal name is. The supervisor board to keep those two Linux devices functional. So it does a couple of things. One, it just maintains in its little microprocessor the state of these guys. It knows these things about it. It can watch, we have logic that watches them boot. And so if they fail to boot 2 or maybe it's 3 times in a row, we actually chose these are Odroids from a South Korean company with an ARM processor in them. We chose these because most of the single board computers out there just have one storage device, like an SD card, like Raspberry Pi has one SD card. And so you're kind of screwed if you corrupt that. These have 2. So we can use logic to say, it took you, the last 3 times you have not booted, so we're going to hit your boot select pin and have you boot from alternate media. And then we're going to rebuild your SD card from here. So that was a big part of the project. So these are 2 of, I think we designed 4 boards that we have now made for us. And then that's where the complexity gets. So you make mistakes we added a whole bunch of complexity, which means that that's like also adding failure modes. So there's this kind of whack-a-mole with single points of failure, and then trying not to trip yourself up by adding complexity to fix this, but then having a problem in your logic for the complexity. So we've been working through that, and that's one of the reasons why I'm glad we only put a couple dozen up over the wintertime, because we found some things in here that we wanted to fix that weren't triggered until, in one case, until the temperature dropped really cold. This is what it actually looks like. I mentioned the sensor harness. So this is the harness that hangs down inside these white Stevenson shields. You can see the window for the camera. Here's the camera here. There's supposed to be, I guess this is the microphone over here. This is a Faraday cage because the printed electrochemical sensors are super sensitive to RF. And so this is our gas, there's holes in it. This is our gas sensor. That board that I showed you on the previous slide that we made, the sensor board is sitting right here. This is a particle sensor. And then inside the blue boxes, you can see the manager board here. We replaced the heat sinks on these Odroids, there's another one underneath, with aluminum blocks that are pressed against the outside because we were concerned about heat. And we now are kind of relaxing that and deciding to go with a slightly larger box, not an aluminum box, because we found aluminum changes temperature quickly enough that you get moisture forming on the inside of the box, which is not something you want to have happen. So let me kind of wrap up so we have some time for questions and tell you how this has gone now, trying to put stuff out in the public way. The privacy policies, we started with a draft. We sent it around to privacy experts. We sent it to EFF and ACLU, and then we had a workshop and worked through the policies with them. And then we had a 6-month comment period with the general public, and we captured every suggestion and question and critique and addressed all of them in a document out on the website. We had public meetings. The next one is actually October 18th, and that's the flyer that's going out. And it was in those public meetings that we would talk to people, we'd serve them dinner, talk to them about the project, what we're trying to do, because we really want this to be a partnership with people in the city. And in fact, the design of this was a collaboration with the School of the Art Institute of Chicago, and they actually taught a course around the design of this device. And they said, we gave them some goals, and they hit 2 of the 3, but the third one we'll hit later. The first was conspicuous. We want it to be very visible, not hidden. The second is we want it to be sort of friendly and inviting looking, and I think we kind of hit that. The third, we haven't hit yet, was we wanted people to be able to interact with it even if they didn't have an electronic device mediating that interaction. So some physical interaction of some kind. We haven't done that yet. We have some ideas on how to do that, but the main reason we haven't done it is we ended up putting these at 20 feet above the sidewalk. That turns out to give us a better angle for the camera. I mean, if it's lower, then you can do like shoe studies, but you can't see the intersection. But the other is that we started working with the union electrician shop in the Department of Transportation are putting these up. That's Brian, by the way. And one of our first meetings, we said, we'd like to put these things at like 6 feet off the ground because we have some ideas on how the general public could interact with our device. So as soon as they picked themselves up off the floor from laughing, they said, we don't think you're going to get the kind of interaction that you have in mind. So there's sort of like, trust us, we have stuff out there. So we put them out of baseball bat range, but we will put some down lower and sort of take the risk. And we're also working with the School of the Art Institute of Chicago about some kind of device that might wirelessly connect to it, but be, strapped around the pole that you might be able to interact in some way. Anyway, so the partnership with the city, we also have done some curriculum, when I said that these sensor projects are high school projects, I said that with the experience of having helped 100 teams do projects over the last 2 years. So for the second year in a row this year, and then we'll do it in the spring with funding from the Motorola Foundation, we did this sensor curriculum with students at Lane Tech High School. 8-week curriculum, and it starts with, hey, what's your science or policy question that you need to measure and collect data about? And then what's your data measurement and data collection plan? And what sort of sensor and device do you need? And then you build that device, a wireless sensor device with some commercial pieces. Then you place the sensor out, each of the teams, for 2 weeks and collect data. Then they come back and they learn how to analyze that data and answer the question they started with. So we're trying to teach them not just how to build stuff, but how sensing and data-driven science and policy can work. This year, if you go to hackster.io, this year a new requirement was put on these teams here that they write up their project in hackster.io. So you can go there if you have a high school kid at home, and you can pick one of these projects and reproduce it, because the code is there, the wiring diagrams, the bill of materials, the explanation, the goals of the project, et cetera. So with that, then when we do this again next year, we'll have a set of projects that we use to then have workshops with high school teachers around at least the Chicago area, and then allow them to be able to do this kind of curriculum as well. A couple things about the relationship with the city and with the residents of the city. On the right-hand side, I already mentioned aesthetics were important, so that's what it looks like. This is at State in Washington, I believe, near Macy's. So we think we sort of hit the aesthetics okay. Open source was really important. We want this platform to be usable by others, and of the over 100 universities and cities that have contacted us, only a handful have wanted to actually open up the technology and do something with it. There are people that want to do that, but the vast majority of folks we've talked to just want to use it as is to measure stuff in their city. Quick replacement, I've already talked about being able to inject new sensors and other devices, anything smaller than a hockey puck. But you can see, along with this Evo camera here, you can see everything is, even this, not this, but even like a walk sign is connected with 2 stainless steel straps. And we worked with, this is Bob on the left, we worked with Bob and his team to design the mounting system and the enclosure. We made some changes to the enclosure for just practical things like that's gonna tear the skin off our knuckles when we put it up, so can you move that out of the way? So the quick replace the goal was you, Bob, and your team, you should be able to replace one of these with just as much time and effort as it would take you to go and replace holiday decorations, which they already do. So after we get the 500 in, we have in our contract with the city that they'll replace 100 a year for us. So we've got a long runway where we can keep injecting new things into the city, as long as we can afford to build 100 new ones and upgrade them. This is the first 100 locations. About 24 are up already. There are 40 devices in our lab at Argonne that are just finished going through kind of a burn-in that will go over to the Department of Transportation next week. And they're hoping to get up about 8 to 10 per week. We'll see how that goes, because their work schedule is dictated by weather and how many people crash into poles that they have to repair and that sort of thing. But the goal is to get all 100 of these up by January or so. We'll see if we can hit that. The color coding, it comes from this kind of rule of 3 as to where we put these. The first thing we want, so all 3 of these things have to be true. Number 1, people who live in that area of the city need to be interested in something that's relevant to the device. Maybe it's air quality, maybe it's noise, maybe it's traffic safety, maybe it's lake effect on air quality or weather. But we want residents to be interested. Second, a group of scientists funded by someone else, because we're just an instrument builder, who would take data that gets collected about that particular issue and maybe give some insight into it. And the third thing that needs to be true before we'll put something on the map is that somebody in local government is also interested in that particular issue. So the purple ones on this map come from Vision Zero program. Those are high accident corridors. The red ones come from a project called Compass. It's compass.uchicago.edu. That is a cohort of 4,000 families across the city, and among other things, they're studying asthma. So we're putting them in those locations there. So it's all kind of driven by science, residents, and government. And then we also have a web form so people can request a node or a set of nodes. It doesn't have to come from the city or science team. And there's one that's up in this area here, I believe. There's 3 of them on there that come out of that web form. And one was from a crossing guard who said, hey, I'm helping kids cross the street in this really busy intersection. There are not supposed to be large trucks, but there are. So I can call the city every day and complain about this, or could you put one here and start collecting that data so the city's got the data and can respond to it. And I guess I'll also say here, I often get asked, what are the ways the city of Chicago will use this instrument? And one of the first things that the city wants to do, and all of the projects I've talked about are kind of rooted in Rahm Emanuel's vision for the city to move from reactive policy to proactive policy. So they're looking at this as a kind of an early warning system to be able to respond to a problem either before it gets to the level that people will complain, like noise, for example, or before they hear about it from someone calling it in, like a flooded intersection, because you can't rely on people reporting problems because everyone thinks someone else is going to report that problem. So to have an early warning system like that is one of the things that the people in the city of Chicago are most, or the city is most interested in. So just to sort of close here, next steps on Array of Things. We do have this team that's in place. Rao Kodamarthi, who you probably know, Bill, from EVS, is on it. An atmospheric chemist from DePaul, some people from UChicago, Luke Anselin is involved. The EPA, it's actually the Cook County EPA, and then City of Portland has a air quality expert as well. So that's a big part of what's happening is over the next few months, really getting a handle on what those experimental air quality sensors are telling us. Design upgrades, lots of pilots that are happening. Each of the pilots here are also driven by that rule of 3. But the first requirement is that there's a team in place already that has a university or national laboratory in the city working together. And if they don't have that, then they show up on this map as the yellow and blue because they're not quite tall enough for a project like this. The red ones are teams where there is an existing collaboration between the city and a university or a national lab team, and they've identified a science or policy question for which an Array of Things deployment would actually help them. So this is sort of where we are. We've got one up, actually one was up in Seattle, and then we had them send it back so we could give them an upgraded one, and it's not been sent out yet. 2 of them are up in Denver. There should be 10 of them up by the end of this month. Hopefully you'll see them if you go to SC. And then Chattanooga should be green because we've got some up there as well. So our goal then is we've decided to set the goal over the next few years of 100 cities with 100 nodes in each city, or 10,000 total. And the reason for that is not to sell these gadgets, although we will sell these gadgets, but it's really to develop a way to measure 100 cities across the globe which differ in size and geography and climate and economics and level of development, and to pull that data into one place where we can analyze how these cities are working and compare something in Delhi with Denver on a sort of apples-to-apples basis. And I guess I'll close by saying we are also really, really actively pursuing partnerships with other projects that are collecting data, particularly sensor air quality projects. So we've got a partnership with Academia Sinica in In Taiwan, they have something called Airbox with 3,000 PM2.5 sensors around the island of Taiwan and South Korea, including one that's hanging outside my daughter's apartment in South Korea, collecting PM2.5 data. And so we're talking to them about how we make sure that any data we collect here, besides being open, can actually be integrated with theirs and vice versa. So I'll close there with 6 minutes left for questions.
Thank you.
He's coming with a microphone.
Very impressive, great work. Know about your project. I just want to bring up that last week we had a different colloquium speaker, Wendy Chun, who raised some issues, and I just want to raise a couple of those issues here. The project was well on connecting weather and crime, of course, became very politicized. That came out in Chicago Tribune. How you ask the question around the data can in fact create inferences about the data of the city. So that's one thing, and I know that you're concerned about these areas. The other is that we have consistently come up in big data discussions is, what about the lack of inclusion of data and the implications that you analyze a city, but not all the city is being equally censored? For example, if you look at where the cameras were chosen, they were funded to be put in areas that basically were poor, south, near
about
west
the safety
side.
cameras in Chicago?
Yeah, but you can just look, and the Gold Coast area simply is not censored as much for any of the data. So there's implications there in terms of there's lack of data in some of the areas, and then there's a lot of data and a lot of surveillance in other poor areas. Are you involving social scientists in these questions? Because the organizers in the communities and the local cities may or may not address some of those social science implications and the bias by lack of inclusion.
Yeah, I would love to talk to you for an hour about this, but we maybe can talk about it later. But so let me just respond to a couple of those things. So I didn't mention when I showed the crime prediction, first of all, that's a spatial prediction. It's not a prediction about a person or a house. It's just an area. There has been controversy, and still is controversy in Chicago, all around policing. And even things that the police department is doing that is in good faith, they're trying to make things better, it can come across the wrong way, and there's, of course, bad actors as well. On the right-hand side of that graph that showed the crime prediction, I didn't mention there's a company that Brett now is funding and starting. And all of the algorithms that were used there are open algorithms. And we, not just for that work, but for all of the analytics work, we feel like it's essential that the algorithms are open so that they can be analyzed and to look for what biases we might have built into the algorithm itself. So open algorithms is really important for those kind of predictions. We do, one of the co-investigators of the MRI grant is Kathleen Cagney, who runs the Population Research Center at UChicago, which, and then we also work with other parts of the university that are doing urban science, like Crime Lab, which is run by Jens Ludwig. And he has, in Crime Lab, has a program that's addressing youth violence on the South Side. We have relationships with community organizers. There's a community organizer from the South Side named Stephen Philpott that is on our executive advisory board. And he's an organizer on the south and sort of southwest part of the city. So those are really important to us, those kind of connections with communities. And that is partly what drove that rule of three. Let's make sure we're partnering with the community to give them data about their neighborhood rather than be sort of watching their neighborhood. You mentioned the disparity between, say, the Gold Coast on the west and the west side, which you see if you drive through Chicago. A lot more potholes. Sort of potholes tend to correlate with poor neighborhoods for some reason, right? With the data science, there's some hope that from early results that we can help the city do a better job of delivering services in a more equitable way. What happens, and Dan O'Brien from Northeastern and Rob Sampson from Harvard did the study of 311 service calls in Boston, and they found that there is a frequency bias. The higher income neighborhoods call more often. In some neighborhoods, they just don't use 311. They use 911, but they don't have time to complain about a street light being out or about a pothole like somebody that lives in the Gold Coast. The woman that's in charge of this group, they're actually called the Rat Patrol. They go out every day and they set rat traps and baits and things like that where people have called 311 and complained about rat infestation. So the woman in charge of the Rat Patrol reported back to the chief data officer that when they started sending the crews out based on predictive analytics rather than responding, they found the worst infestation she'd ever seen in an area where nobody would call 311. It's like on the south side. And so that gives us some hope that if we could, first of all, make sure we don't have biases in the algorithms, but if we could start to use the data to drive city services rather than the squeaky wheel, we will see some equity in some of these services. I mean, we can't solve the whole problem. It's not a technological problem, but we can at least help.
Thanks so much. This is really impressive and exciting. I do a lot of work in cities in the developing world, and looking forward to talking to you about that later. Apparently you are as well, which is fantastic. And I wonder, given the strategy for citing these, well, first of all, I'd be interested in what the cost is. So what is the cost that you're quoting? Because I want to get a sense of how big can this array be made.
Pilot projects are $6,000 per node.
Okay.
That's more than it costs us to build the hardware, but it includes the communication and support and,
It's not a leasing model, though, because some of these are going to go out. Okay. But the second, I think, more interesting question involves the use of data and its importance for building civil society and making government more responsible. So in many parts of the world, we have concerns about the way that intentional lack of service to particular populations. And in those places, I would imagine that this kind of information might be extremely beneficial, but not consistent with the interests of the local government. So you're not going to have the local government coming and asking for these. In fact, you may have the local government rejecting this or creating boundaries and obstacles. And I'm just wondering how you think about that, where you're going in that respect.
Well, to be honest, because I'm a techie, I think about problems like reliable electricity and Wi-Fi, which are daunting in those areas. But we also have worked, we just brought Luis Betancourt in to run a new institute. Luis came from Santa Fe Institute and has done a lot of work in unplanned settlements and some of the issues that you're raising. I'd say we're kind of sneaking in on some of these places. We are about ready to do a pilot project. We did a pilot in Chicago, or are doing a pilot in Chicago with 20 indoor and 20 outdoor air quality monitors going out to 20 of the families in that 4,000 family cohort. And we just submitted to an internal funding mechanism to do a project with 100 homes in 10 different parts of a particular Indian city, where we're going to put an indoor monitor and outdoor. This is why we got to figure out how to do non-Wi-Fi, like LoRaWAN or something like that. So we're not going in and saying we're going to instrument your city. We're going in and instrumenting homes, which will eventually also instrument the city. Maybe we'll run into, I just don't know enough about it. So it's like my answer to your question, Donna. We are trying to provide tools and technology to people who know what they're doing and who work in developing countries or who are social scientists that work in the city of Chicago, and kind of follow their lead.
Yeah, I work on the far south side of Chicago, and I work in areas of transportation. And I'd like to see about how we can get ahead of the curve in terms of future use of this technology to support community development. As you may know, there's a large infrastructure project called the Red Line Extension from 95th Street to 130th Street out to Alkell Gardens, arguably the most isolated public housing project in the nation. Number one, air sensors around Alkell Gardens provides a very serious political issue in that you have nearly 24 waste management sites. It's where the city dumps its garbage. So there would be an issue about air quality around there, and I'd want to know how many sensors are down out there. And the city already knows about this, so it's not like you're going to be informing Rahm Emanuel about a problem that he doesn't already know about. It's a question of what he'll do about it. The second question, more important question to me, is this. Our concern with the Red Line Extension is the degree to which, and I want to see if the technology could be predictive in a way, the degree to which transportation, mass transportation to this area would stimulate gentrification of the area, concern that many residents have. And so I want to see how, working with the CTA, the city, neighborhood community organizations that I work with, whether something can be done in terms of looking at the movement of property values, what would happen with transportation in relationship to the 4 different station stops suggested. Is there a way, or can you imagine a way in which this technology could be used to gather data to predict the possibility of certain kinds of social, economic forces being either unleashed or mitigated by transportation, since transportation is a major. And just a little last problem, is your system hackable? Because kids on the south side now are using smartphones to hack the blue light system. And I know of some.
I don't believe there are unhackable systems.
Okay.
But our systems, we've taken some pretty strong measures to prevent intrusion and strong measures to detect intrusion. As an example, I cannot connect to any of these devices, nor can anyone on my team, nor can the kid on the south side, unless we make a mistake, which happens, but there's no way to initiate a connection. There's no open ports. We have to wait for it to connect back to us. So that's just an example. It's an encrypted network. So they're designed to use the cellular network to make those connections, and they can only connect to one place. All the code that's running is signed. So there's a bunch of things that we've done to make them as unhackable as they need to be. If the guys who own the black camera underneath ours wanted to break into them, they probably could, but they don't need to. On the red line, that's probably not something the array of things would help with, the kind of question that you're asking, but it is something that the computational modeling could. So if we take a social economic model and we compare that with a transportation model, then we can start to not predict the future, but to at least look at some scenarios that might start to answer that question. And that's where it would be, we do have agent-based modelers that do these kind of models, but they're computer scientists, so it requires collaboration with social scientists to make sure those models are correct. But I would say what you're talking about, you should be able to do that as a computational model. How I don't know the state of those kind of computational models in terms of how useful the prediction would be, if you will, but it'd be worth exploring.
Thank you, Charlie.
Okay.